Cool. Thank you, everyone, for coming and surviving. Was almost the last talk of the day, and more to go. And this presentation is kind of a representation of both tools that the USGS has developed over time, knowledge that we've gained from data collection, and from assessing transport in our aquifers. And the title of the talk is Groundwater Quality, but it relates more to how changes in aquifer quality can be induced by pumping, by agriculture, and by just domestic use. And again, my name is Ramon Naranjo, and I work with the USGS. So the first contaminant or constituent of concern is nitrates. Nitrates have a health and environmental risk to our streams and, of course, human health. What we have found through some of our investigations on the alluvial aquifer in Carson Valley is that nitrate issues that are result in elevated levels in the alluvial aquifer are resulting from domestic use of septic systems. And a little bit of background here is that, our septic systems contain a lot of different types of waste. We dump things down our toilets and our sinks, and a lot of different chemicals in our waste systems are then transported to the soil surface, the unsaturated zone, and then eventually end up in our drinking water. It doesn't actually go away. Some of it doesn't. Nitrate is a particular problem. There's an EPA maximum contaminant level, which has resulted from many years of data collection that they've determined that it results in health concerns to children, to women. Some of the symptoms are listed here: blue baby syndrome, hypertension, diabetes and cancer, birth defects. And in many of our stream systems in Nevada, our stream systems are nitrogen limited. And what that means is that, any small change of nitrate in our systems can induce substantial impacts to our ecosystems. If you've been to Lake Tahoe and you walked along the near shore, you will see, many times you'll see periphyton or algae growing on the surface of rocks. And that's because there is a finite amount of, not an insignificant amount of nitrogen or phosphorus entering that system. And in a lake like Tahoe or in many of our streams, there's plenty of sunlight, and all it takes is just a little bit of nutrients, and you can induce some ecological changes to our stream system. And here's an example of a photo taken earlier. We had a really interesting discussion on invasive weeds, and this is a photo of the Carson River of a harmful ecosystem, harmful algal bloom that occurred in 2012, and as a part of a study that Nancy from our office produced a report on. And subsequent to that report, or before that report, we did some data collection and modeling to look at the distribution of nitrate in the alluvial aquifer. And this graphic here shows the map of that data. This is, again, an older report, 2008 to 2009. And what we found from a large sample of wells that we collected data from, that there was areas where the concentrations were elevated, and other areas around the agriculture areas, the concentrations were much lower. In this investigation, we also took samples to look at stable isotopes, because you can use the stable isotopes of nitrogen and oxygen to fingerprint the sources of nitrogen. And in this study, we documented that much of the nitrate source that we found in the groundwater was more related to human waste, not agriculture, fertilizer type nitrogen. And the conceptual model for the introduction of nitrate to our aquifers is shown here on the lower left, which is basically, residential homes that are of high density, where their leach field is located away from their home. The urea that leaves your home enters your septic tank and then gets distributed along a number of different rows as a leach field. And as that urea enters the soil environment, it does tend to break down, and depending on how well maintained your tank is, or even your septic leach field is, that urea will transform to ammonia. And as it moves through our unsaturated zone, it begin to build up ammonia on the surface of our aquifers. And that ammonia translates to nitrate. You don't excrete nitrate. Animals, if you went to a sewage tomorph and took their effluent, you would find zero nitrate. What you'll find is organic nitrogen. And that organic nitrogen is what's in our septic tank and what's in our leach field. And as it moves through the soil environment, then it becomes mineralized, as was mentioned earlier, or nitrified from organic N to ammonia to nitrate. And nitrate is highly mobile, whereas ammonia isn't. So in areas where there's a lot of septic density, you tend to build up nitrate in the groundwater. And if you are domestic well is in the proximity to your leach field, then you complete the cycle of nitrate in your residential use. What we have found through a number of different sampling and binning of where we find the highest concentrations of nitrate, where there are more septic systems, which is kind of highly packed residential areas, we tend to see higher concentrations of nitrate. And areas that were nearby rural or agricultural lands tend to have lower nitrate concentrations. And it's because, with agriculture, they're not applying, well, in many cases, they're pumping groundwater and putting it on the surface, but there isn't the septic density of homes contributing to influx of urea or nitrate or ammonia, thus converting over to nitrate. So in this investigation, we looked at transport models. We used an existing regional groundwater flow model. We built two transport models in ModFlow MT3D of the Johnson Lane and Ruinstraw areas. And what's shown here is just the general area, 62 miles squared for Johnson Lane, 14 square miles for Ruinstraw. And what matters here is the septic densities. There's 1,400 septic systems in Johnson Lane with about 23 septic systems per square mile. And you can see the difference with Ruinstraw having higher septic density, about 36 septic systems per square mile. There's a 511, at this time, 511 wells at Ruinstraw and 2,627 wells in Johnson Lane. And these are domestic wells at the time. So we use these models that we created to look at different types of scenarios. The graphic on the far left is showing what would happen if business as usual, we continue to use our septic system and domestic pumping of aquifer for Johnson Lane. And this was predicted out to 2059. The areas where you see red are concentrations that were greater than the MCL of 10 milligrams per liter. And you can see the distribution of concentration between 5 and 10, that yellow area. When you look at the first scenario, which is, okay, we decide we're no longer going to use septic systems and continue domestic pumping. And I believe this wasn't an instantaneous cutoff. It was cut off, I think, in 2030 for no septic systems. And so this scenario resulted in the domestic pumping wells removing the nitrate from the aquifer system, which involves basically cleanup through removal from domestic use. The second scenario hypothetical was that you would both remove the septic systems and then remove the pumping, the domestic pumping. And this would be a direct removal of the source and no more groundwater pumping, and you now allow that nitrate to move naturally through our system through groundwater flow. And you can see that the area still exists around, very similar to the domestic, with removal of domestic pumping, in that the gradient up to the north there is so flat, the nitrate concentration just lingers. And I think it's the area between there's a hypothetical fault that was included in the model that we were using, so that that fault was acting as a hydrologic barrier to groundwater flow. But even to the north of there, where it meets the river, it's the groundwater table is very shallow, and there isn't much of a groundwater gradient to move that nitrate out of the system. So it sits there and it remains. So for the Ruinstraw, this is similar type scenarios, but we're looking at a different area. Ruinstraw had a much larger septic density, and you can see that those areas shown in red are related to homes that have been there since the 70s. The longer these homes have been using septic systems, the longer they've been recharging the aquifer of that urea. So, which is indicative of the areas that are non-continuous in terms of the distribution of that greater than 10. It's just that the areas that are associated with those homes are maybe further apart from each other. When you continue domestic pumping and you now remove the septic systems, you can see that the pumping effectively removes all of the higher concentrations. And when you move on to septic systems being removed and no domestic pumping, again, this area is an area where the water table is depressed, so it stays for a much longer period of time. It doesn't actually flush out of the system. Flushing would result from recharging the mountains, moving groundwater flow, and naturally moving that nitrate towards the river. But in this case, because in Ruinstraw we've had substantial declines in the water table, so the gradient is actually not so steep towards the river. So what we know about nitrate is resulting from a number of different studies, and what we know is that septic systems have contributed to the main source of nitrate to the alluvial aquifer. The nitrate concentrations are dependent on well depth, it's the density, and the age of the homes or the septic systems, and the proximity to upgradient systems, which means if you are a homeowner and you're living down the groundwater gradient from an area that has a lot of septic density, you are still at risk because that septic system is going to be flushing through. The high density nitrate concentrations are going to be flowing to the lowest gradient point in the groundwater flow path. Of course, in many cases, if there's a lot of agricultural pumping, that groundwater can be moving towards the pumping wells. But in general, if you're living down gradient of a higher density of domestic use of septics, you're likely to be at risk for increased nitrate concentrations. And what we found is that if nitrate concentrations will decrease rapidly when septic systems are removed, and of course the domestic wells are largely the process for which the nitrate concentrations are reduced. And if no actions are taken, what we found is the nitrate concentrations will continue to increase because along with the age of the homes, for example, the earlier homes that were built in the 50s, they may have been recharging the aquifer 10 years later, so that since the 60s on to now. Homes that were built in the 70s maybe are lagged even further, and so on and so forth. So with a continuum of different developments that have gone in, depending on the age of the home and where its proximity is to the higher density homes, you could still, the influx of urea to the aquifer has likely not been at a steady state. It's probably still continuing to rise, and it's going to be variable according to the age of the residential area. So the second constituent of concern for Douglas, or for Carson Valley, is arsenic. Arsenic, of course, is naturally occurring. The concentrations depend on the hydrogeology of the system, the geochemical conditions, which largely is related to the redox. How much oxygen is in your environment, where the influx of recharge is coming from, if it's ag or natural recharge or the river, all largely plays a role for what kind of concentrations that you might see in a domestic or in a municipal well. Much of the work that we know that is related to arsenic has come from our office. Angie Paul has done a number of different studies looking at in situ remediation of arsenic, and a lot of the data that was collected for that effort was trying to come up with solutions to actually mitigating the nitrate in situ. What I am showing here is a conceptual model of arsenic, which is, when you go to the west, where the granitic Sierra Mountains don't have a lot of volcanic, the geology is granitic in nature, and so the amount of arsenic is much lower. In the Pine Nut Mountains, there tends to be a lot more volcanics. And as many of you know, the redox conditions in those type of environments can be much different from the granitic. And so where you might tend to see different forms of arsenic is related to the aquifer depth. If you're in the shallow part of the aquifer, you might be more attributed to oxidative water, where recharge from ag or from the river or from canals may have influx of high dissolved oxygen, and that creates a different type of redox condition of your aquifer. The deeper you go in your aquifer, your redox is going to be depleted of oxygen, and you tend to get more of the forms of arsenic-3, which is more mobile and more toxic than the arsenic-5, which is found in the shallow part of the aquifer. So for arsenic, data has been collected since the 60s. It's not continuous. What's shown here on the left is the amount of data that's combined here from 1960 to 2015. And shown in red are values that are greater than the MCL of 10 parts per billion, which is much smaller than the nitrate concentrations for nitrate. So what's shown here is that the nitrate distribution is higher towards the east near the airport, and lower in the proximity where the recharge is occurring along the corridor of the Carson River. Since 2016, you can see this is just another graphic showing the distribution of more recent wells. And more of the samples that were collected are in proximity to the stream, but yet some samples collected near the airport are still showing up as values greater than 10. And of course, arsenic is very expensive to treat. If you're a municipal supplier, you have to think about ways to provide water to the public in such a way that it doesn't exceed the standard. The concentrations, again, when you think about the redox environment of an aquifer, again, higher oxygen levels, lower at depth, the concentration distribution of our arsenic concentrations in the aquifer increase with depth. And as what's shown here in the red dashed line is the MCL, and you can see that approximately about 300 feet below the water table is when you start to see concentrations likely to exceed the MCL. So what does this all mean for domestic users? This plot up here shows the distribution of nitrate being simulated by our models. And I showed these graphics earlier. The red or the pink circles represent wells, domestic wells that have been deepened by homeowners. And you can see by the clustering of the domestic wells that have been deepened, they're right around the areas where we see the highest concentrations of nitrate. We don't know for sure why they deepened the wells, because we know that there's areas to the east have had some substantial declines in their water levels. But it's interesting to see that there is this clustering around the areas where concentrations are high. And so since 1982, there's been about 300 wells that have been deepened to about 260 feet depths. So the concentration gradient with depth with nitrate again accumulates through the unsaturated zone, and it hits the water table and it stays near the water table. It tends to decrease as you move through the saturated zone, through the aquifer, because you're depleting the oxygen, and microbes love oxygen, so they're going to go after the oxygen first. They may go after the nitrate thereafter. So naturally, you'll have a gradient of nitrate concentrations in the aquifer. But as I showed earlier, arsenic increases with depth. So if you're increasing your well to 260 feet, you're likely to be moving away from the nitrate that is near the surface. You're now shown here in this nitrate plot, you're moving below that red MCL, as you deepen your well. But at the same time, now you're moving into an area possibly with higher arsenic concentrations. So again, what we're trying to do is build tools that are going to be viable for water managers and for the public to be able to track changes in the hydrology of the system and the water quality of the system. And we've done this a number of different examples for the Walker, which we are calling hydromappers, but it's basically a water dashboard, which allows you to see climate variables that influence SWE that is resulting from near real-time data from government sources. And we put these hydromappers together to satisfy the needs of the watershed. If people are interested, for example, in Walker, there's a lot of water accounting that goes on. They have to track stream flows pretty precisely so to ensure that people are getting water to their respected water use. So we built one hydromapper called the Walker Basin Hydromapper. Again, it uses real-time stream flow and diversion data, and they use this to track water as it moves through the system. We just recently developed one for Lake Tahoe, which accounts for all, and it's our LTEM program. If you're not familiar with it, it's a program that we've started since the 80s that we have been collecting groundwater, stream flow data, nutrient data, sediment data to track progress of the environmental restoration program for Tahoe. And what we wanted to do was build a tool that we could use in support of that data collection effort, which is tracking stream flows, tracking loads, tracking lake stage. And we built these tools to allow us to look, as Chris pointed out, we have SWE periods like this year that looks like 2013. If you're a water manager and you're like, I need to know what we expect our sediment loads or our nitrogen loads to our lake, given the amount of precipitation we had, we built this tool that allows us to look at the hydrograph comparisons. And we use this very similar approach that Chris pointed out with their tool that allows you to compare this year's water year SWE to a previous year, and you pick the year that you enjoy the most representative comparison, and then that you can go into dive deeper into the data to look at what happened with SWE, what happened with stream flow, what happened with loads, and then you can look at clarity. Of course, everyone's concerned about lake clarity, and it all responds very on a seasonal basis depending on the precipitation. For Carson Basin, we have the same vision. We need to track stream flow. We have to track groundwater levels in nitrate and arsenic, and we also have Lahontan reservoir stage. And in addition to the inflows that are coming in from the Truckee Canal. So what we're trying to do is build this tool, because if you are a water user, a public, a person just interested in science or interested in water resources, there are a number of different websites that you will have to go to kind of get a complete picture for what might be happening within your watershed. And what we have found is that there's a lot of really great resources that are available for tracking weather patterns, snow, precipitation, but they all exist in different locations. We build these tools so that all the data that is important to the basin is in one location, and we're hoping to combine all the real-time data that's collected for precipitation, snow. One thing I'll say, during Caldor Fire, as the fire was encroaching in the Tahoe Basin, we had an active fire boundary map that was being updated daily. So we could watch the progression as it was entering the basin, and we have all our stream flow turbidity sites, so we can track what kind of impacts the fire was having in near real time with respect to the Caldor Fire. So that was a really great example of having something that is beneficial for us as scientists, but also for the public to kind of keep in tune with what might be happening in these catastrophic events. But our hope is to build one that incorporates water level data that the state engineer is collecting. And I'll talk a little bit about that. We have our USGS groundwater monitoring network that we have been collecting data since the 80s for water level, and since the 80s for water chemistry. And not a whole lot of arsenic that had been collected over time, but nitrates there are. For the Nevada Division of Water Resources, they collect about 24 wells in the Carson Valley area with no chemistry being collected there. But as I showed in earlier, we know something about the transport of nitrates. So we're going to include some suggestions on where we think additional wells would be needed to kind of safeguard domestic home users, or even better track the progress of nitrate as it's moving towards, if it's moving towards the municipal wells. As an example of that, for the Johnson Lane, this is data that has been collected to date since 1985. And you can see the one area, what's shown in the map is the data from 2008 to 2009, the comprehensive sampling event that occurred. But again, we're collecting 11 wells in this area. This is just a small representative sample of the data sets that we get. But one way that I'm hoping that we can display this information is in a singular graphic like this. As data is being collected, these plots all automatically get updated so that you can be looking at the latest information. And again, for this one example, we see that the concentrations in that one particular well have been increasing. They're steady above the MCL. Doesn't appear to be increasing, approaching the 10 milligrams per liter, whereas the well that's adjacent to it is still increasing. Here's an example where a well was deepened. We're monitoring the well. The concentrations were steadily rising. The homeowner decided, for whatever reason, to deepen their well. And again, as I demonstrated earlier, when you deepen the well, you're likely not going to see much nitrate in that well because of the distribution of concentrations within the aquifer. So the concentrations since then have been close to zero. We don't know what the arsenic levels are in that well. The trends in water level is shown here from the state's website. There is data that's being collected. We want to combine it with our data in one singular graphic so you can see a better, broader picture of what's going on. I will just point out that the data from the Division of Water Resources dates back only to 2014 or 2013 in some wells. So it's fairly recent. When you look at the data that's been collected from the USGS since the 80s, you get a different picture of what's happening to our water levels. And again, here's a graphic showing 28 to 25 feet of decline out in near the pine nuts. And when you get closer to the river, it fluctuates about 2 to 3 feet. It responds to in-stream flows, which are getting recharged from the river. So what I will say is that we have historically been involved in a number of investigations in the Carson Basin and throughout Nevada, USGS. And there are some ongoing studies that we're hoping to finish up within the next couple of years. The one I just described now is just a summary of the trends in nitrate and arsenic in groundwater levels and the development of this Carson Basin Hydromapper tool, which will hopefully be online in the next couple of years. The second study is evaluating the effects of groundwater management options in water resources in the Carson Valley. And that goes back to the transport models that we used for Carson Valley. We're going to revise that groundwater model. That model has since been revised. We're going to use that tool to investigate different water management pumping scenarios. And in doing so, then we have to think broadly, because we know that there's this response that may happen with as a consequence of groundwater withdrawals to the water quality of that water that you're pulling out. There's another study that's evaluation of water use in the Middle Carson. And we're also looking at climate change impacts on those water resources. Both of these models, again, are tools that are going to be used for water managers. We're hoping that we will have some workshops coming in the next year to explain our progress and to explain the objectives. But that is, Ed will actually be formally announcing those soon. So in summary, nitrate and arsenic are two constituents of concern. There's probably more, but right now I'm summarizing the nitrate and arsenic levels for this report. Water table declines are pretty substantial to the east of the Carson. And they contribute to a lot of challenges for domestic well users because they're deepening their wells. They already have issues with nitrate, and by deepening their wells, you run the higher risk of pulling in arsenic-laden water. And so we need a better monitoring strategy for arsenic for those domestic well homeowners so that we kind of get a better understanding of what those risks are. The USGS is actively developing and using groundwater models to help managers guide their decisions for water resources. And we have to understand that the availability of water, where it's coming from, where it's recharged, and how it's being used is all tightly coupled to the chemistry. The chemistry is tightly coupled to the water use. You cannot use water if it doesn't meet drinking water standards, and it's very expensive to treat. So current studies will use our models to better attempt to guide our water resource managers on where and how much water they can pump. And again, we hope to have some stakeholder meetings to describe what our objectives are and to keep the public and others informed on our progress. And that's it.